video, I'm going to talk about the method of initial rates. The method of initial rates is used to determine the rate law from a given experimental data. As I said in one of the previous videos, rate laws cannot be determined just by looking at the balance equation. They must be determined experimentally, and the method of initial rates transforms that data into the rate equation you want. And I will be using an example to illustrate the method of initial rates. So we have a table with the given data, and the question is, what is the rate law and what is the constant k? Let's first try to understand this data. An experiment was performed, and the experimenter used 3 different trials. And in each trial, he wrote down the concentration of the reactant A, the concentration of the reactant B, and finally we have the rate that the reaction followed. And this rate is in molar per second. And the concentrations A and B, of course, are in molar. Now for the actual method of initial rates. The first step you want to do is to find 2 different trials in which the concentration of the reactant is the same. So trial 1 is not similar to any of the other trials, but trial 2, however, has the concentration of B equal to the concentration in trial 3. After recognizing those 2 trials, you want to write each in rate law format. Rate law format is the rate is equal to K times the concentration of A to the alpha times the concentration of B to the beta. Let's do that. So for trial 2, the rate is equal to 4.20 times 10 to the negative 3, and that is equal to K times the concentration of A, which is 6.80 times 10 to the negative 4, that is to the alpha, times the concentration of B to the beta, that is 7 times 10 to the negative 5 to the beta. For trial 3, we had a rate equal to 1.70 times 10 to the negative 2, that is equal to K times the concentration of A, which is 13.20 times 10 to the negative 4 to the alpha, and the concentration of B is exactly the same, 7 times 10 to the negative 5 to the beta. And the third step involves dividing the bigger rate over the smaller rate, or faster over slower. So we will be dividing the rate of 3 over the rate of 2. That will be 1.70 times 10 to the negative 2 over 4.20 times 10 to the negative 3. They have the same units, so they will cancel out. And we have K over K. For rate 3, it's 13.20 times 10 to the negative 4 for alpha. 7 times 10 to the negative 5 over beta. To the beta, sorry. And 6.80 times 10 to the negative 4 to the alpha. And then the same goes for 7 times 10 to the negative 5 to the beta. So out of this, we can cancel this 2 out. They're exactly the same. We can also cancel the k constants. And then this just becomes a simple division. They will be equal to 4 is equal to, this gives us about 2 to the alpha, Let me go to the next page. So we had 4 is equal to 2 to the alpha. The way this is solved is by using a natural logarithm. We add it on each side, so we'll get ln 4 is equal to ln of 2 to the alpha. This can lead to the alpha going down, meaning that it will be ln 4 is equal to alpha times ln of 2. We then solve for alpha, divide ln 4 over ln 2, and that will be equal to 2. So now we know that for reactant A, the order is second order. So right now what we have for our equation is that R is equal to K times the concentration of A to the alpha, which is 2, so that will be squared, times the concentration of B to the beta, which we have to find now. And to do this, we simply follow the same steps as before, but we add a 2 instead of alpha. So that would just leave beta as the only variable. And you can choose any of the 3 trials. So I'll be using trial 1 and 2. The rate of trial 2 is again bigger than the rate of trial 1. So we will get trial 2 over trial 1. So it will be 4.20 times 10 to the negative 3 over 5.25 times 10 to the negative 4. And that is equal to K times 6.80 times 10 to the negative 4. That is squared times 7 times 10 to the negative 5 to the beta. Then we divide everything over the rate over reaction 1, trial 1. So that'll be K times 3.40 times 10 to the negative 4 squared times 3.50 times 10 to the negative 5 to the beta. These two cancel out, and then we can divide the rest. That will be equal to 8 is equal to 2 squared times 2 to the beta. So that will be 8 is equal to 4 times 2 to the beta. We divide that. That will be 2 is equal to 2 to the beta. Same as before, we add ln on each side. The beta goes down, and that leads us to beta is equal to 1, because it's ln of 2 over ln of 2. So now we can actually say and write the Rayleigh law for this equation, or this reaction. That would be R is equal to K times the concentration of A squared times the concentration of B to the 1. So you can just leave it like that. And this is third order overall. Finally, to get the constant K, you simply use this Rayleigh law and plug in the values from the data. So let's use trial 1. Let's first solve for K. That will be R over the concentration of A squared times the concentration of B. And for trial 1, that is K is equal to 5.25 times 10 to the negative 4 mole per second over the concentration of A squared, 3.40 times 10 to the negative 4 molar squared, and finally times the concentration of B, which is 3.50 times 10 to the negative 5 molar. This is 1.29 times 10 to the 8 reciprocal molar squared, m to the negative 2 times reciprocal seconds, reciprocal time, and that is the constant K. So thank you for watching this video. I hope you liked it and found it useful. And if you did, please be sure to give it a like and subscribe to see more videos like this one.